Okay, so we're ready to start looking at our next module, which is Module 5. And Module 5, you're going to see here in our learning plan, we are going to be looking more at Chapter 13. So we've been spending some time here in Chapter 13. So the next two sections we're going to be looking at are going to be 13.3 and 13.4. I'll be pulling up this PowerPoint in just a little bit. Additionally, there's going to be just one section in chapter 17. So 17.2, we're going to be looking at to round out this module. Oh, my mic keeps going in and out. Oh, it's quiet. It's going quiet for me. Does anybody else have a problem hearing me this evening? Just kind of looking. Anybody else having an issue? I don't. All right. I'll try to go close to my microphone on my computer so that hopefully, thank you. So hopefully it'll be a little bit better for you. I'll get my piece of paper off of here. Okay. Got quiet for a second. It sounds better now. Okay, then I will pull this closer. Thank you. Thank you. Okay, so we are going to then be rounding out module 5 with chapter 17. The next time we will meet, we will be finishing up with 17. So we'll be spending two class times together on module 5 for preparation for the application problems. You'll notice down here that we have some sample problems and another problem in chapter 13 that are going to serve as our practice problems. These are the ones we're going to focus on getting through tonight, okay? And then we'll have a little bit of 17 left for the next time that we get together. Just want to peek over at our application problems. So as we look at the Module 5 application problems, there are 7 of them, okay? One of them is going to be redoing one of our sample problems with some changes. So I'll discuss that when we start looking at these. But these are going to be the problems that we're going to be using to reinforce the ideas and the concepts that we have in Module 5. So I'm going to go back a level and we will pull up our PowerPoint. And we'll start talking about what we see in chapter 13. Zoom out a little bit here. So as we know, in this chapter, we're looking at energy and momentum. And actually, officially, we're going to be looking at momentum this evening with these last two sections in chapter 13. So we know, probably from physics, actually, it should be from physics, that when we have an impulse is going to generate a change in momentum, okay? And I know that as you guys have been going along, you have used and seen the impulse momentum theorem, okay? And that's what we're going to be using for the problems in module 5. So we know that momentum is equal to mass times velocity, okay? So you'll notice here that we have our impulse. Impulse is equal to force times time. So that's what we have over here. And impulse is just represented in our overall equation as IMP. And momentum initial plus an impulse is going to be equal to a momentum final, okay? And it's really not complicated to calculate or to really relate to momentum. It's really just mass in motion. And in order to change that momentum, we have to engage with a force over an amount of time. So, so this is something that we actually probably experience multiple times during the day. And so it's very relatable. That's why I like momentum. It's one of my favorite subjects actually in physics. Now, here are the units that we would expect in the metric system for impulse and for momentum. So impulse, because we're going to take force times time, is going to be a Newton times a second. Now, if we take a Newton and we expand it out as a kilogram meter per second squared, and we multiply it by seconds, we end up with a kilogram meter per second, which, if we look at momentum, you'll notice here, momentum is mass, kilogram, times meters per second. So a Newton second is a kilogram meter per second. And so that's how we can, if you would, add and subtract these together, because they do have the same units for both impulse and for momentum. Now, let's look at impulsive motion. So impulsive motion, and impulsive forces that are on a particle are going to cause impulsive motion. Now, I think it's easier to talk about non-impulsive forces first. A non-impulsive force is going to be a force that is on a body that is not going to affect the momentum. And many times, and in the case of, for instance, is baseball that we see here, the weight of the baseball is negligible compared to the force that a bat would be hitting it with to change its momentum. So for instance, a baseball in its initial state is going to be pitched towards a batter. In the middle part, the impulse that is going to be given to that baseball is going to be the bat hitting the ball. That's the force. And it's going to have a time where that ball is going to have contact with the actual bat. And that's going to be the amount of time that it's actually in contact. Now, there is weight, as we know, on that ball, and that is a force that's acting on it. But like it says here, it's not considered part of the impulse because it's not going to really change, how the final momentum is going to react on our baseball. So that's called a non-impulsive force. So at times, we're not going to be including the weight because of that, okay? So we're going to just look, in this case, you're going to notice that our impulse forces are going to be based on the horizontal plane here, not on the vertical plane. Now, our first sample problem is going to be sample problem 1313. So oopsie, I'm so sorry. It looks like Jason had a question. So as long as it's quick enough, correct. Yes, that is exactly correct. And if you go in and you take time to read the chapter, they say it almost exactly like that, Jason. Yes, it has to be quick enough in order to be negligible, right? Mm-hmm. Now, our first sample problem is going to be 1313, but before we get into this, I thought it would be good, just like we always do, let's kind of jot some of these ideas down and the relationships that are going to come in handy as we get started on these problems. So what I'd like to do is start our equation sheet, and this is going to be for the section 13.3. We will be adding to it because there's another section after this 13.4, but it's a good idea to get started as we get into these problems. So I'm going to go underneath my camera here. I'm going to pull this over. And we are going to look at, I'm going to call this Module 5, Chapter 13, equations. And you could even call it impulse and momentum. Okay. And this is going to be the items related to section 13.3. Okay. Now, in order to create a change in momentum, we need to have an impulse present. So in kind of a generic sense, impulse is equal to change in momentum. Okay. Now, if we expand that out, impulse really doesn't have an official variable. So in the book, they just use like IMP, and we'll see that in a little bit. But impulse is calculated simply using force multiplied by the amount of time that the force, I have seconds here, I'm sorry, I was thinking units. Force times time, the amount of time that force is going to be applied to the body in order to, now we're going to set that equal to mass times velocity, which is the momentum after, so kind of like final, if you would, after the impulse is given, minus the momentum before. Okay. So that's the change in momentum, Now, just like we had for, other quantities, we're going to take this negative and we're going to put it on the other side. And kind of the standard way that we're going to see the book actually write this is we're going to say the summation of all of the momentums present, and we're going to call this velocity 1, So this is going to be like our initial or before, okay? Plus the summation of all of the impulses, and that can come from an applied force. It can come from weight if that ends up being one of the forces that are causing or changing the momentum. But like I said, when they're short, then we don't worry about them, like in the case of a baseball being hit by a bat. And then equal to, and then we're gonna have the summation of mass times velocity 2, which would be like our final or our after. Okay, so it's really just rearranging this and kind of putting it into that format that we've seen in a couple other places. Now, couple things. Number one, momentum and impulse are vector quantities. So what that means to us is that positive and negative are a real thing, right? So and I think for all of the problems that we do, positive is going to go to the right and up if we have any Y forces. So we are going to be needing to define our convention as we move along so that we know why we have positives and negatives, okay? Now also, when no external force acts on a body, the impulse drops out. Now, this will make more sense when we have one or two examples where we're going to see this happen, okay? So I'll identify those when we do the sample problems. But when there is no external force, then this impulse simply cancels out, and then the equation just reduces to the initial equals the final, or really the conservation of linear momentum is actually what it reduces to, okay? Now, I also think it's important to look at units here, okay? So let's look at the units that we're dealing with, okay? So for momentum, now it's funny because momentum 2 doesn't seem to have any like official variables. And so I usually just kind of either write it out, or you may see it in other texts as a capital P, but capital P is used, typically for power and things like that. So we're just going to kind of write out momentum or show it in the version of M times V, and then impulse as F times T. Okay. So the units for momentum are going to be, for metric system, kilograms times meters per second, okay? Mass, kilograms times meters per second, right? And those are the official units. They're not shortened to be called anything. It's just kilogram meters per second, mass times velocity. And then for the English system, there's a little bit more to this one. So we know that when we want to find mass in the English system, we need to take its weight in pounds divided by gravity. Okay, so I'm going to do pounds divided by feet per second squared. Okay, that would be our gravity underneath. And then times velocity, which would be feet per second. Okay. Now, as you can see here, our feet are going to cancel out when those two multiply together. And then my seconds squared are in the denominator of the denominator. So they multiply on top. So one of these seconds is going to get rid of one of those seconds. So this ends up being pounds times seconds are going to be the units in the English system. Okay. Now for impulse. Okay. Impulse, the units in the SI system are going to be newtons times seconds, because impulse, as we know, is force times time. So newtons times seconds. Now, for it to be added to momentum, it has to have the same units. And kilogram meters per second or kilograms times meters per second are not the same as Newton seconds, or are they? Okay. So if we expand out the Newton, okay, if we expand out the Newton, a Newton is actually a kilogram times meters per second squared. And then we multiply it by seconds. So if we look, the seconds squared and the seconds would cancel out just one of those. So we end up with a kilogram meter per second, and that's why we can combine it with momentum. Okay, so it ends up actually being a kilogram meter per second. Okay, is a Newton second. It's equivalent. And then for our SI or for our English units, it would simply be force times time. So it's going to be pounds times seconds, which is the same units for momentum. Okay. So just in case you were wondering about units, or if you need to add them in, I wanted to go over those with you so that you could see how the units kind of shake out or what we're expecting for each one of those quantities. Okay. All right, so that's really the information I want to cover for section 13.3 as far as equations. We'll be adding to this because we are going to be looking at section 13.4, so there'll be more that we want to put here. But for right now, in the first couple practice problems that we have, this will be helpful. Okay, so with that, what I will do is our first practice problem is going to be sample problem 13, and that can be found in your book on page 862. And I do have it on the PowerPoint here. And what we have is we have an automobile. It weighs 4,000 pounds, and it's driven down a 5-degree incline at a speed of 60 miles per hour when the brakes are applied. And it says here it's causing a constant total braking force of 1,500 pounds. Determine the time required for the automobile to come to a stop. Okay. So if we look underneath, we'll kind of get started here. So we are going to start by saying sample problem 13. This is found on page 862. Okay. The weight of that vehicle, okay, so I'm going to say WA for the weight of the automobile is equal to 4,000 pounds, okay? The velocity one that it's actually going at this time at the start is going to be 60 miles per hour. We were told that there's a braking force of 1,500 pounds. And our final velocity 2, we want to know when this is going to come, how long it takes to come to a stop. So that means that our V2 is going to be 0. We also know that we are going down an incline of 5 degrees. Okay. And we want to find T, the amount of time to stop. Okay. Now, our approach, we're going to use this impulse momentum theorem, okay? So the impulse momentum. So I'm just going to add approach. There are other ways to do this, and we've done similar problems to this, maybe not in the exact same, variable format, but we're finding that we have, 3 distinct approaches, if you would. We have we have Newton's second law. We have, well, actually 4, conservation of energy. We have the work energy theorem, and then now we have impulse momentum. So depending on what you have going on, you usually use more than one will still get you a good answer. But for this one, we're going to use the impulse momentum that we just learned here in section 13. So that means that we're going to be looking at MV1 plus the summation of the impulse. It's going to be equal to MV2. And the only reason we don't have the summation in front of either one of these is because it's just going to be the mass of the vehicle times its velocity, and the same thing at the 2. So there's only really one body, if you would, that we're dealing with. So, but we'll see that those multiple forces that are going to affect things. Now, first things first, for our velocity one, we're given 60 miles per hour. So we need to convert it to feet per second. So I'm going to do that right here. So V1 is equal to 60 miles per hour. I know in 1 mile, there are 5,280 feet. Okay. So miles cancel. And in 1 hour, there's 3,600 seconds. Okay. So now I'm in feet per second. So I'm going to take 60 times 5,280 divided by 3,600. And we should get velocity one equal to 88 feet per second. Okay. And that we're going to need up in this equation. All right. So it kind of takes care of that. Now let's look at kind of a diagram of our situation here. So just like in Newton's second law, where we kind of sum the forces and we set it equal to the mass times acceleration, and we draw two different diagrams equaling each other, we're going to draw a diagram for each one of the steps along the way here in our impulse momentum. So I'm going to start by drawing, and the car is just going to be this rectangle. I'm just going to draw the rectangle. This is going down that 5-degree incline. And this is going to be the mass A times velocity 1. Okay. And what I'm doing is I'm setting my coordinate system. So this is going to be my Y, this is going to be my X, and that's going to be like the positive direction. Okay. And you'll see why in just a minute. So this is going to be like the X axis, if you would. Then I'm going to say plus. Now, this takes care of the mass times velocity 1. All right. Then I'm going to draw the automobile again. And this is where I'm going to identify the impulse, okay, and the forces that are acting. I'm going to go through the center here. I'm going to draw my X and Y axis. So this would be, if you would, my X and my Y, okay? And in this case, we do have a significant weight, and it is going over an amount of time. So we are including the weight in this one. So this is going to be WA, okay? Now I did exaggerate the angle, and the angle that this is from the Y is 5 degrees. Okay. Now, you'll also notice that going in this direction, I'm going to kind of go over the top of my X. This is going to be the braking force. So it's moving down the incline. The braking force is going opposite that. And it is going to act for an amount of time, right? To bring everything to a stop. So this is the braking force times the time. Now, the weight is also going to have a component going down the incline, okay, during that same amount of time that the braking is happening. So what we need to do is we need to figure out what is that component of the weight that is going to go down the actual incline. Hold on, I'm going to lift this up here a little bit because I see that there's a little bit of a glare, okay? So this right here is going to be the component of the weight going down. So I'm going to call this WAX because that's the X axis. Now, I'm going to draw another diagram a little bit larger of just the weight. So if I look at this in terms of that X and Y, okay, so here's my X, here's my Y. Here's the application of that force of the weight coming down, okay? If I extend that further down and draw that weight here, okay? If this is 5 degrees, okay, so this is my weight, this is 5 degrees, right? So if I want to get the component to the x-axis, which is the one that we're trying to find, this would be my WAX. Does that make sense to everybody? So kind of this is that force right there, right? Along the x-axis. So now to get that, right, to get that value, that means that if this is 5 degrees, this is going to be 85 degrees. So you can either take the cosine of 85 degrees or the sine of 5 degrees multiplied by the weight to get that x component. Okay, so we go down here, we can say WAX is equal to, I'm going to take the sine of 5 degrees because that was the value that was given to us in the problem, times the weight coming down, right? Aren't you glad you guys learned about components? It's like a big part of your engineering career. And if we multiply the weight, which is 4,000 times the sine of 5 degrees, we should get 348.6 pounds. Okay. So that is the number then. That is the number of the amount of that 4,000 that is going to act going down the actual incline for the amount of time that it's going to take to stop. So we want to multiply that by time. Okay. And then we're going to set this equal to then our car. Okay. And this is going to be mass A times velocity 2, which is actually equal to 0 because this is when we come to a stop. Okay. So what we're going to do is we're going to take what we have here and we're going to put our numbers in, right? Any questions so far about the diagram or how we got the the weight of the automobile X component here? Okay. All right. So we are going to take then this equation up here and we're going to kind of expand it out. So this is going to be mass of the automobile times velocity 1. Now, as I said earlier, remember that momentum and impulse are vector quantities. So their positives and negatives are going to come from the direction of the convention. This is going in the direction of positive X. So this is a positive value. If you want to put the positive out front, but positive assumed, right, as the first value there. Plus, so now we're going over to this diagram. And I'm going to start with the WAX quantity times the time. Okay, I'm going to put that in parentheses so we can see that that's a separate variable. Now that is going down, so that's why it's positive. Now you're noticing that our next vector, which is going to be the braking force, that is going up. And if we look at the direction that it's going, it's opposite the positive X. So this is going to be minus FB times the time. Okay, so those two elements are what's affecting the impulse. Okay, and then we're going to set that equal to 0 because our maybe I'll do this. This would be mass A times velocity 2, but this goes to 0 because it's going to be coming to a stop. So now we can put in our values and our only unknown we're going to find is going to be our time. Okay, so for our mass at A, we're given 4,000 pounds. So that is a force. So we're going to have to divide that by gravity. And we're in the English system. So this is going to be 4,000 divided by 32.2. That's going to be our mass. Times velocity 1. Velocity 1 was the 60 miles per hour, but we're going to use the 88 feet per second that we converted it to. So it's going to be 88 plus the X component of the weight, which was 348.6 times time. And then minus 1,500, which is the braking force, times the time. Okay. And we're going to set that equal to 0. So our only unknown here, as I said, is going to be the time that we need to find. Okay. So go ahead and solve for T in this problem and we'll compare. Okay. Christian got, yep, same number as I did. Excellent. 9.49. Excellent. Hopefully everybody else got that same value. Excellent. Good, good, good. Okay. And that's what we were looking to solve for. How much time it took to get that automobile. Excellent. Isaac got the same thing. Good, good, good. Going down that 5-degree incline with a 1,500-pound braking force. It'll take us almost 10 seconds to get that to a stop. All right. Questions on that problem? All right. Now, I have a little note here. This one is going to parallel nicely with application problem 13, 139. All right. Just so that you know, that's one of the application problems that I picked for you guys. So that one's gonna work well for that. Now, since we're going to be doing another sample problem or practice problem, what I'm going to do is I'm going to stop the video here. And then I'm going to start a new video with the new application or the new practice problem, and then we'll continue on.